Okay, so I very happy to be here, and congratulations, Ras. And as I was saying, I liked very much the title. Certainly, Ras has quite a few elegant results in probability, as many of the people present, well, let's say all. I felt obliged to speak about something elegant, and well, I have a couple of elegant results in probability, but they don't come every year, unfortunately, and this is not one of those years. So I would rather try to talk about how we tried to prove an elegant result and this didn't work out, or hasn't worked out yet. Maybe one of you can give me a hand. So I will try to speak about how we try to do percolation on square lattice, and with the additional handicap that we want to do it in an elegant way, not just any way, just necessarily elegant way. What I would say that we made a few, so that's a joint work with Misha Christoforov, and I would say that we did have made a few interesting observations, and maybe eventually they would be enough to do it. And well, we tried it. Actually, we tried it in several different ways, and I think this year for about 4 times we thought that we could do it, but then we could not do it. And again, unfortunately, this is not one of the weeks when we think we can do it. It's one of the weeks when we think we cannot do it. And also tried it in 2 different ways. And I will speak about the first one, which is trying to move the proof for hexagonal lattice to the square lattice. So it was for a while advocated by Van San Bifara, and he advanced quite a lot in that direction. So it's a bit also based on what Van San Bifara suggested to do at one point. And what he suggested to do is that we try to start with a proof on hexagonal lattice, or well, triangular lattice, which is dual, and observe that much of it works for any Trivalent graph. So we would sort of move this proof. So the first step would be to move this to the lattice, which is called, I'll say a few things in a minute, lattice which is called bathroom tile lattice, this one. So this is also a Trivalent graph. So the nice things, if you do percolation on those, so let's say percolation, placket percolation. Oh, and I presume that in this room I don't, well, who knows what percolation is? Okay, now who hasn't raised his or her hand the previous time? Well, there is obvious contradiction. But essentially, the model which we do here is that we cover randomly in 2 colors, yellow and blue, the hexagons in this picture with probability equal to 1/2, and that's a theorem of Kesten, rather Wehrmann deduced from Kesten that it's the critical probability. So the nice thing about Trivalent graphs is that there is some sort of a duality. So if you have a box, well, any shape, any rectangular shape, topological rectangle, you only have a horizontal crossing of yellow hexagons which are adjacent to each other, if and only if you don't have a blue crossing vertically. Now, if you take probability of yellow equal to 1/2, probability of blue equal to 1/2, then the model is invariant with respect to taking the negative. So in this case, what you get, so it's just, so we study crossings, and the probability of having a vertical crossing in one color would be the same as, so it exists if and only if there is no horizontal crossing in the opposite color, because it would form an abstraction. But since the colors, you can flip the colors, that's the same as the 1 minus probability of horizontal crossing in this color. So in particular, if you have a symmetric shape, so some shape which is basically square, which is symmetric given that lattice. So for example, for hexagonal lattice, it has to be either a rhombi with angles 60, 120, or a square which is rotated by 15 degrees or something. So if you have a symmetric shape, then you get that probability, you can rotate it. So then for symmetric shape, this is also the vertical one. You get that probability of vertical crossing twice is equal to 1. So the probability, regardless the size of the box, is 1/2. And this basically shows that PC is equal to 1/2. So we started with P probability of having a black hexagon is P. Probability of blue hexagon is also, we take also P. So if we take them 1/2, then we can do this trick that these two are the same. And then from this we deduce that regardless the size, for any size, probability of crossing is 1/2. Now, why did I do all this thing? Is just to say why it's, if you haven't seen it before, why it's logical to take the probability of 2 covers being equal to 1/2, because you get a model where something interesting happens on big scale. So for any big square, probability of a crossing is exactly 1/2. From this, it's not difficult in 2017. Well, it was difficult some 40 years ago to deduce that if you have non-symmetric, so from this it's called Russo-Seymour-Welsh theory, that for non-symmetric with fixed ratio of sides, so for example, it's size, this side x, A fixed, that probability of this is bounded away, well, let's say constant of A is bounded away from 1 and 0, so hence something interesting happens. And the big question is whether this something interesting is conformally invariant. So the big question, for example, whether these and other things have conformally invariant limit. So whether the probability, for example, if I fix a shape, I superimpose a hexagonal lattice, and I tend the mesh of the lattice to 0, whether this tends to some function of some function f of a, which is function of conformal models of rectangles. So in this case, it's just of a. So this is what we know, and I'll say in a few words how we know. So it's we know it here. No conformal invariance. But the proof is essentially, well, at least it's, when you look at it first, it very essentially uses the rotational symmetry by 120 degrees. At least that's the first impression, and I'll try to convince you otherwise. So the plan of which was suggested to by Van San is that from this we move to percolation of plackets on this. Again, the same thing. So it's the same thing. We cover these plackets, which are either octagons or rhombi, independently with probability 1/2 in 2 covers. And we ask what one can say about probabilities of the crossings and whether they have a limit. Now, the difference between these two is that this is a very symmetric lattice. It's transitive way. Well, you can map any hexagon to any hexagon, any vertex to any vertex. Here it's also sort of. It's basically the simplest lattice after hexagon lattice. You can move any rhombus to any other rhombus, any vertex to any vertex, but you already have 2 different types of faces, so it's slightly more difficult. And then the next step would be that what you do, you keep the same PC. Well, that can be done in 2 different ways. But you take P equal 1 on every other hexagon, every other rhombus, P equal to 0. Well, yeah, maybe I use the same cover, it's better. p equals 0 on every other, and you keep for octagons p equal to 1/2. So what this does is that in one cover, let's say in black cover, this rhombus connects these 4 octagons, and this one connects these 4. But in black, these two disconnect them. On the other hand, they connect them in another cover. So if you look at it carefully, this is exactly the same as doing the following thing, that I will just draw an evoke of this picture, that you cover edges instead of octagons. So every octagon corresponds to an edge. Let me just plot it here. So this is the picture to which it corresponds. And what you do, you cover edges with probability 1/2, blue or yellow, and the octagons which are p equal 1 octagons, they collapse to vertices, and the others, they sort of go to faces. So this is the Bond percolation. This is the percolation on Bond on the square lattice. Okay, so so the idea is that we first, Van Sant's idea was that first we transfer this proof to this lattice, and then we somehow push p's around. That can be done in several ways. For example, one can continuously move p's here from 1/2 to 1 and to 0. And when I first saw it, I was very excited, and I was telling to Van Sant that this is the difficult step and this one is the easiest step. I still think so, but they are both very, very difficult. I cannot do either one of them, but I still think that sort of I have more ideological difficulties with this one. With this, I kind of can convince myself that it should be like that, but it's very difficult still. So what I will say, I will try to say a few words about how properly to look at this proof and try to adjust it to this one. So I will forget altogether to passing to the square lattice. And essentially what we'll start with is that we define the following function. So we take some domain. So it can be any domain. One should think that there is a triangular lattice, well, hexagonal lattice superimposed upon it. Well, yeah, it's much easier to draw the square lattice. That's why we want to do it. And then you mark 3 points on the boundary. Let's see, j plus 1, and j plus 2. So we modulo 3, we number them. And 1 point inside, let's say z. And we say that hj of z is the probability that there is a crossing of hexagons of a given cover. So I'll just draw some small circles, which has z on one side and j on the same side, and j plus 1, j plus 2 on the other side. So we have these 3 functions. So each function is a probability of separating z and j from the 2 other vertices. So there is h1, h2, and h3. And then there is another function, which, let's say, I will define as tj of z. So this is the probability. And now, well, let's say, so here it gets a little bit trickier, because we take point z, but we have to also fix a vector from it, let's say zz prime. So it's, technically speaking, it's a function of zz prime. And then what we do, we ask that there are crossings in 3 different covers, which go like that. So around a point z on a trivalent graph or on hexagonal lattice, if you take point z here, there are 3 hexagons. So we can start 3 paths, and we just ask that they are not all of the same cover. So again, there is parameter j, j plus 1, j plus 2. So I want to make a small remark, which is very important later, that here it's a function of z, just probability that z is below, above the lowest crossing, so to say. And here it's a function, you can draw the same picture, but with the arms which spiral 120 degrees more, where this arm which starts in this direction lands not on this side, but on the next side. And it will be a different probability. Of course, if you have thought enough about like percolations and easings, if you have very, very large site and you do anything like that, they will spiral logarithmically often. So probabilities of T1 and T2 will be approximately the same, and in the main term. But then the rest, and the rest will be important for our story, will be different. So it also has a kind of importance from conformal field theory point of view, that the first term it just doesn't see the domain. It just tells you in how many ways three arms can escape from one point in the plane. But the second term, on expansion, it already sees the conformal geometry of the domain, conformal modulus of 3 points on the boundary and 1 point in the middle. Okay, so here actually comes a very elegant idea, which I won't describe more, but there is a trick by Eisenman, Duplantier, and Aharoni, which says that this is well defined. I haven't specified the colors of the arms. I haven't said whether it's blue, yellow, yellow, or blue, blue, yellow, and the colors of the arms are not important. It's just important that they are different colors. So it's well defined regardless the colors. So we can change the colors, and essentially it is the same trick as was used here with the negative. So what you can do on this picture, we will have another point of view on this later, which is somehow more conceptual. So if you look at this picture, there is this black arm and this blue arm. And you can choose their realizations which are the closest to each other. So out for this given picture, out of all the pictures, we choose, out of all the black arms, we choose the black arm which is counterclockwise closest to blue, and blue which counterclockwise closest to black. And now the observation is, and it's sort of standard trick in percolation, it similarly was used before by Kesten many times, but in different circumstances, that then these two arms only depend on the space between them. So if I change something here, it doesn't change the counterclockwise most arm. It only changes this one. And once I fix these two, I am free to play as I will with the rest, so I can swap it to negative using p equal to 1/2. So I can change the color of this blue arm in this configuration. And then I can integrate all configurations, and I get that the probability of this picture is the same as, for example, the probability of that picture. Okay, I will return it back to blue. So the important thing which I have used here is that the p is equal to 1/2, but I use that these arms, they are not all of the same color. Because if they are all of the same color, there is no canonical realization of them. So imagine a spider web, and in spider web from the center you can go to the boundary in many different ways. How you choose 3 canonical ways? There is no 3 canonical ways, because you can choose the ones which don't spiral at all, the ones which spiral many, many times. And here there is a canonical way to choose. If arms are not of the same color, there is always a canonical way to choose them, and this allows for the flipping. Okay, now a very important remark is that this object, being a probability of some event, is of the order 1. Because it's just probability of some event, which, well, we have just argued about Russo-Seymour values. The probability of crossing a box of a fixed modulus is between 0 and 1, separate weight from them. So it's something of order 1. Now, this object, it's again follows from Russo-Seymour values. Let me say that delta is the lattice mesh. So this is a probability of order delta to some power. So actually from conformal field theory we know that it's 2/3, and for hexagonal lattice we can prove it. But from Russo-Seymour-Welsh, we can just show that it's, well, at most some power epsilon. So this is an object of much small probability. And basically, if you haven't seen Russo-Seymour-Welsh before, then what one does, here we get a crossing from scale delta to scale 1. But we can split it into several annuli. And to do this crossing, we are required to cross each of these annuli. And the number of annuli will be logarithmic in delta. And each crossing of each of these annuli will give us some definite factor. So we have definite factor to the power logarithm of delta. So we get some, so this is the probability, it's like constant to the power logarithm of delta, which is delta to some power alpha, which was advertised. And if you know conformal field theory, then you know that it's delta to the power 2/3. But it's just important for us that it's a small exponent. And then there is a observation that in some sense derivative of hj is equal to derivative of tj. So if I take hj of z minus hj of z prime, then this will be tj of z prime z minus tj of z prime. So in a sense, you can say that derivative in the direction of z prime of function hj is equal to derivative in the direction z prime minus derivative of z prime tj. Now, why it is so? So I'll give a different proof in 10 minutes. But essentially, what happens when we consider difference of these probabilities for two nearby points? The difference will be written in terms of events that one point is separated by a crossing and another isn't separated. So if two neighboring points, one is separated, one isn't separated, then there is a crossing which passes in between them. So you get already this picture. But you cannot select a lower crossing, which means that there is an abstraction, so you get exactly a three-arm picture. Now, what this means, essentially it means that derivative of hj is derivative of tj, but why did I put quotation marks? So hj is a function of a point. tj is a function of a point in a direction. So here it's not exactly that we can fix direction, but then we get not one function tj per point, but we get several depending on the direction. So it's not like derivative of hj is equal to derivative of some function tj. It's in one direction it's equal to derivative of one function, another direction derivative of another, because otherwise if you say so hj is of order 1, so derivative is of order delta. If you subtract 2, if you assume function is smooth, and we can actually prove that it's smooth from Russo-Seymour-Welsh, then difference of values nearby points, distance delta, will be around delta. So this is of the order delta to some power, unknown power epsilon. So this derivative is delta to the power 1 plus epsilon. So if this is literally true, then it means that on the scale of h, its derivative is exactly 0. So it is exactly 0, because its derivative is smaller order than it should be. But it is not exactly true, and what is happening ideologically? Yeah, maybe I will say in 5 minutes what is happening there ideologically. Yeah. So another way to look at this, and maybe a more appropriate one, was suggested by, again, Weinson, that we should check, not look at the function hj and function tj, but we should symmetrize it. So we should, let's say, denote by tau cube root of unity, and then write f of z equal to some tau to the power j hj, and let's say s of z prime z is sum of tau j tj. So what we do is that we sum 3 of these functions with a coefficient 1, cube root of unity, another cube root of unity, and these 3 functions also with different widths with the very same conditions. And then again we can write the same thing, that derivative of f is derivative of S, but again, one has to put quotation marks. Now, what is the theorem we know in hexagonal lattice? So far, it's all true for any trivalent graph. So for any trivalent graph, you can write these things. So for hexagonal lattice, we have a theorem that as mesh of the lattice goes to 0, the function f tends, as mesh goes to 0, function f tends to function f small, which is the conformal map of our domain on an equilateral triangle. And one can also show that its marker is not so good. Okay. Well, bad marker. And hj, and if you write it in a better marker, hj goes, as mesh goes to 0, to the projections of f on tau to the power j. So tau to the power j is those three vectors. So basically, it goes to projection on this vector, which is 0 on this side, 1 here. The other one, 0 on this side, 1 here. So basically, well, maybe the remark is that hj, they tend to harmonic functions, which are defined by the fact that there are 0 here and 1 here, and there are 3 complex conjugates, so to say. So the more symmetric way is to say that there is a unique conformal map of our domain on an equilateral triangle. Why? Because by Riemann uniformization map, we can map on a disk. Disk can map an equilateral triangle, and we have 3 points and Möbius transformations, 3-dimensional family, so we can move them to the angles. And it turns out that our 3 functions are just kind of this mapping written in 3 coordinates of 3 cubes of unity. So they are a little bit, so these 3 functions are linearly dependent. But, well, a more symmetric way to work with them is this. And the way the proof of this goes, so maybe the proof, is that you show that hj, well, that f is almost discrete analytic. And then you pass to a limit, and you show that in limit it's analytic, and then you define the boundary conditions. So before speaking about this, I want to rewrite it in a different way. And what one son observed is that there is one thing which we can show for every lattice. So it's one son bifara. So for every lattice, we can show, we cannot show that sum of tau j hj tends to something, but we can show that this sum tends to 1. And this is a non-trivial statement. It's actually, because what is it? It's a sum of 3 probabilities for a given point z, and one is probability of such a crossing, another is probability of such a crossing, and the other one is the probability, what am I missing? This crossing. So it turns out that the sum of this probability is not equal to 1. It's not equal to 1, but it tends to 1. And why this works on every lattice and this works so far only on hexagonal lattice is again because of this identity which is with question marks. So this object is, as I said, of order 1. This object is of order delta to the power 2/3. So it turns out that if we plug in sum of hj here, then on the right-hand side, we can get rid of the dependence on the direction. There will be no dependence on the direction. And we will just get a theorem, well, that derivative of sum of hj in any direction is equal to derivative in the same direction of a function which is 1 order smaller, or 2/3 order smaller. So in the limit, it disappears completely. So we get that the function in the limit is constant. And you can easily check that this function, if you sample it on the boundary, for example, if you sample it here, well, let's not on the boundary, let's sample it here. If you sample it here, then these two functions will be 0, and this function will be 1. This will be 0 because you can't separate this point, it's on the boundary, and this will be 1 because there will be infinitely many ways to separate it. Okay, so now I want to pass to some new stuff, and I want to sort of explain how to look at it, or at least how we try to look at it, and to connect it a little bit with the last talk of today. And the observation is that we want to do it somehow more conceptually and more in the spirit what we're doing for self-avoiding walk or Ising model, more in the spirit of disorder operators in conformal field theory. So we want to rewrite this in terms of the O of 1 model. And it turns out that both of these things, they are rewritten very neatly. Only you have to do O of 1 model with some branching. Now, maybe a big question. Yeah, so I raised the big question. So basically, again, what was the percolation? We cover hexagons or domains on our lattice. And then the partition function is the sum of 1 over 2 to the power area of our domain. So if we have domain of area 10, there are 10 hexagons to flip covers. So the probability of given constellation 1 to the power 2 to the power 10. Okay. Now there is a O of 1 model, which is, so here we have just hexagons of 2 different covers. So what we do here, if we have hexagons of 2 different covers, we draw an interface between them. And of course, the interfaces, they all will be either loops or will end up on the boundary. So here we have collection of loops. And again, we have the same function because, well, in other models of N models, we would count how many loops we have or what is the length of loops. But here we look at the particular case where we don't count this. We just have that. Now, suppose that we will want to do the tricks we have did with conditioning on part of the picture. So when we condition on the part of the picture, so let's say we do with conditioning, well, let's say on omega, then we get here, we get in the first case, 1 over 2 to the power area of omega. Now, suppose that here we want to condition on some loops. Yeah, okay. On some loops, let's say gamma j. Then the weight will be 1 to the power 2 area of one neighborhood of gamma j's. And this is basically easy to see. It's the same thing as before. What do I need to know that, suppose that I want only to condition that there is this loop. In terms of coverings, I don't need to know this cover. I only need to know that these two are different, these two are different, these two are different. And then the loop passes here. There is a possible factor of 2. You might want to fix cover in some place, but essentially this is the function. So conditioning works the same. So if you condition on loops in some area, it's like taking weight 1 over 2 to the power area, not length of the loops. You might want first to put length of the loops, because if you draw a loop, in percolation, if you start drawing a loop, when you come to some hexagon, you flip a coin. If you have blue on the left, yellow on the right, you flip a coin. If this is yellow, you turn left. If it is blue, you turn right. So you might think that if you go along the loop, with each step you toss a coin. But sometimes you arrive to hexagons which are already visited. Then you don't have to toss a coin because you already know which cover they are, if they already touched our loop on the other side. So essentially, it's not length of loops, it's area of one neighborhood of them. And with this observation, it turns out that we can rewrite in a nice way both of these two things. And Hj in the other model, Hj of z, is just the probability that, so we do the model of one model where the boundary data is that there are three sources at these 3 points. So there are loops which start at these points. And then there is another loop which starts at z. And if you connect 4 points by loops, there are several ways to do it. So Hj is a probability that the connection will go like that. Now, as you wish, you can either draw other loops and say that all configurations are equally likely. Or you can just draw these loops and weight by 1 over 2 to the power area. That will be the same. So basically, drawing these 2 loops, it fixes cover in the one neighborhood of them. So let me maybe just, it fixes cover in this area. And then flipping cover in the other areas, you can get other loops. Or you can draw other loops in the very beginning. Now, the tricky thing is here that the picture I have drawn is not exactly completely legal in terms of percolation configurations. Because if you walk around this point z, blue becomes yellow and yellow becomes blue. You get to negative of your vote. So it's essentially a picture in the percolation which is branched over this point. But it's completely legal in terms of loop configuration. So we just do that. And if you look at Tj of z, this you can guess it would be just the probability that there are these 3 things which end, well, I'm not very good at drawing, which end at z, and the one which goes to j, it starts in the direction z prime. Now, well, this is just a rewriting again, so it should not like a priori give anything new, but it makes the thing more comfortable to work with, and occasionally it actually gives some new things. For example, a small remark, immediate remark. Well, maybe before I do the remark, I need to say a few words. Well, yeah, lemma, these are the same definitions. So why, for example, these 2 definitions are the same? So let's say so suppose we start with the original function hj, and we take this crossing. Now, what does it mean that there is this crossing? It means that if I start here and I start exploring so that blue is on the left and black is on the left and blue is on the right, I can never cross this crossing. So whenever I explore, I will bump into it always. So it means that eventually I will end up at this point. And to make it all legal, I will cover the outside of the domain black here and blue here. So if I have a picture on the left, then it has a built-in interface which runs between the points j plus 1 and j plus 2. And this couples it with the configurations on the right where these 2 points are connected. And then if these 2 points are connected, so this is basically a coupling with a configuration of loops where these 2 points are connected, but then I have only 2 points left, so they have nothing else to do but connect between themselves because the other 2 are already occupied. In the other way, it's also, suppose that you have this picture. What you can do, you cover just the immediate neighborhood of this thing. And you get the picture on the left, which has this blue crossing, because the blue crossing which just will go on the boundary of that. Again, the probability will be the same. So it's basically the same trick that if you have a covering, you uniquely get interfaces because they separate covers. If you have a family of interfaces and you cover one hexagon, then you can start covering each time flipping the cover when you cross the interface. So this is the coupling which is very easy. And the only tricky point here that you don't want to start it with this point, because around this point there is some branching. So we want to work with a nice side where there is no branching and only later go to the branching. Okay, so is this sort of clear why these two partition functions are the same?
Can you explain again why Z is not separated by a blue loop from J?
No, look. This picture by itself, it gives you a picture like that where there is no connection of Z to something. To have connection of Z to something, you need to introduce branching. And in this original picture, there is no branching whatsoever. So what we do, we take the lowest blue thing, we play with this as we would, but then we completely resample this part, putting branching in this point. And the branching has to go on the boundary. So we play, the nice thing about percolation is that you can resample something independently of the rest and there are no boundary data. So it's always this trick that you choose the lowest crossing, everything above is independent. So this is what we do here, with the only exception that here we resample it not as a percolation, but percolation with branching. But independently, you can just, what you can do, you can start with this model. You can work with it, you can prove that these things, they have conformally invariant limits. But then you can connect it to percolation, because if Z is on the boundary, if Z is taken on the boundary, then it's a legitimate percolation configuration. You don't have to have these funny thoughts what is going on. So in principle, the other point of view is that just you play with this picture without thinking what they mean. You prove something, but then when you take Z on the boundary, you get information about the original percolation. Okay, so, how long are the talks? Okay, well, that's not the answer to my question, but that's a difference of two answers to two questions I was going to ask. Yeah, okay. Okay, so I will just write two observations which you can make with this. And one observation is that just Hj, sum of Hj plus sum of Tj is exactly equal to 1. And this is a trivial observation, because what you do, it's equal to the partition function when you have these 3 points. And when you write the partition function with these 3 points, what can happen if we start interfaces from these points? How can they possibly connect? And they can either connect, that 2 of them connect and one lands here, but also they can all land in the middle. And this gives us T's, and this gives us H's. And the total sum is 1. Partition function is just probability of event. So what we get, that actually not Hj doesn't tend to 1, well, it does tend to 1. But just there is a specific thing which when you add to it, it's exactly 1. And the specific thing is much, much smaller order because it has 3 arms, and by Roussel-Mersch is smaller power than delta. But the other thing, which is perhaps much more interesting, so let me just write this, that we have this relation that df zz prime is equal to ds zz prime, where f is symmetrized H and this is symmetrized 3-arm thing. And we can stack these relations. So what we can do, so basically we have that difference of f between these 2 points is equal to difference, well, minus, there is a minus sign here, minus difference of s between these 2 points. But s is again, it's defined not at a point, but a point with a vector. In this case, we can have to put vectors inside. So we can stack these relations. So we can stack them. And you can write things like that, that you, for example, we have our lattice So you can have different journeys in this lattice. So for example, we can have this journey. I will tell in a second what that means. So we can have this journey, and the difference of f along these edges will be equal to difference of s along these edges. So again, s everywhere. But then what we can do, we can stack them with coefficients. If we stack them with coefficients 1, then f will cancel out, and you get the difference of f at two endpoints is equal to certain sum of s's, which won't cancel out because they have different rotations in different vertices. But you can also stack them with coefficients so that s cancels out. And then you get the sum of f here. And stacking with coefficients so that the s cancels out, one can get interesting relations of f. And what I will write, that there are two kinds of relations. There are exact relations on f, on any trivalent graph. And what I will write is what happens if we do the bathroom tile lattice. So for example, this is the exact relation that if you sum f with coefficients 1, 1, tau squared, tau, minus 1, minus 1, minus tau squared, minus tau, that sum of, well, let's say f with these coefficients is exactly equal to 0. And the other thing is that the sum of f with the coefficients minus 1, 1 is equal to sum of s with the coefficients minus 1, 1 the other way around. And here it's I square root of 3 minus I square root of 3. Now, and this is a thing of lower order, and for this particular thing we can show that it is of order delta squared. So actually, apparently I made notes for 1 hour and 30 minutes talk, not for 45 minutes talk as usual. But as you say, as I said, s is of lower order. And actually this is, again, this is a small lemma we can prove. We can prove that s is of order exactly delta. So s has additional cancellations compared to 3-arm exponents. So with some 3-arm exponents rotating, then we get exactly delta. So this is exactly delta squared, and this is a priori something of bigger order. So what, for example, this gives from what one can get from that, that if I take I cube square root of 3 f of northern vertex minus f of southern vertex, this is essentially a derivative of f from one western vertex to another, and that we can show that this is, because these are vertices of the same type, this is essentially lattice mesh times derivative in the direction x of f, or the limit thereof. So basically the bottom line is that if you look at it in this way, you get more freedom to operate with it. And you can stack relations, and you can get two types of relations. And you get exactly 1/2 of what you want to, either on hexagonal lattice or on any trivalent graph, you get exactly 1/2 of what you want for Cauchy-Riemann relations. So I've written what you get on bathroom tile. But on hexagonal, it's also only 1/2. But you get many more which are approximate up to some error written in S. And it's kind of a bad miracle that this doesn't work out. Because we have many things which say that this sum of f, which is like derivative sum of first order, is actually of much smaller order. So this is this plus O capital of delta squared. But it's not clear, so what we convinced ourselves that the first order things we get are not enough. But you get a bunch of second order things with O of delta cube, and that we don't know yet. So basically the question, and it's maybe a question for Hugo's talk, so if you have exactly 1/2 of exact relations, but then you also get, well, 2/3 of approximate, can one try to push it somewhere further? Yeah, stop.